And we're back. I can't remember if we actually balanced this first one out, so let me go ahead and actually show you what it looks like. So when we go through and predict, we should end up with this, with our overall formulas. We can then go through and balance that equation. Barium shows up the same on both sides. Chloride, I've got 2 on the reactant and 1 on the product, so I need a 2 to make that 2 chlorides as a product. I can look at my potassium. There's 2 potassiums on the reactant side, and there are now 2 potassiums on the product side because of that coefficient 2. I have 1 chromate and 1 chromate. Remember, the 4 is part of the name of chromate, like A is part of the name of barium. Okay, so we now have that balanced equation. You may potentially, well, actually you probably aren't thinking it yet because we haven't gotten to it, so let's just let that slide. Let's move to the next equation. We've got aqueous sodium chloride, so sodium is Na, chloride is Cl. We know it's aqueous because we're told it's aqueous. We need to balance that equation, or that formula. +1, -1, our formula is balanced. We've got a reacts with aqueous lithium nitrate. Lithium is an Li. Nitrate is NO3. We know it's aqueous. Lithium is a +1, nitrate's a -1. That balances. This then needs to go through a double replacement reaction. Notice we'll know it's a double replacement because this is the only type of reaction that has this kind of setup. None of the other reactions have this format. So we'll swap them around. We'll end up with sodium bound to our nitrate, and we will have lithium bound to our chloride. Balance each of those formulas. Sodium is a +1, nitrate's a -1, so that balances. Lithium's a +1, chloride's a -1, so that balances. Now we can balance the whole equation. So we go all the way back through. Typically a good idea to erase all your charges, particularly if it's a show your work kind of question. Just happen to see lithium first, 1 and 1. Then we have sodium, 1 and 1. Chloride, 1 and 1, and I'm out of space, we'll just write nitrate over here. Nitrate, I can do 1 and 1. Like we did with the chromate, nitrate we can do as a complex ion because it doesn't change in the course of the reaction. It stays nitrate. It's either lithium nitrate or sodium nitrate, so we don't have to worry about that. So if we want to organize that and make that look nice and pretty, there we go. We now have our 2 equations. And as soon as I drop that 2 back in there, we'll have them balanced. So what I was previously alluding to is that you'll notice that when we did the prediction for that second equation, I didn't specify any phases in my answer. And when we balanced in the last video for that first equation, you'll notice I didn't give you any phases then either. Yet, when we look at the answer, what do you see? Well, shoot, there's phases now. What's going on here? This is a bit odd because you're asked to predict the products, which means you need to know if the phases are correct or not. So that becomes problematic. Why and how do we know in our second equation they're both aqueous, and in our first equation one's a solid and one's aqueous? Okay, we need to come up with some way to know that. Unfortunately for you, it means more memorization. Okay, we have to follow certain rules to go through and do this. Okay, those rules are known as your solubility rules. When it comes to exam 3, I will give you a condensed solubility rule sheet. Okay, and that rule sheet will be missing a couple rules. Okay, the rules that it's going to be missing would be rule number 1 and rule number 3. Okay, I won't give you those 2. And the main reason being, you should memorize those 2. If you've got those 2 memorized, you're pretty well set for a lot of your predicting ability. Okay, because those are hard, fast, always true. We never worry about those. If you see an alkali metal, so group 1 metals, or the ammonium ion in a compound, we know that compound is soluble in water. And soluble in water translates to the phase of aqueous, which we abbreviate as AQ in an equation. Okay, same deal with the nitrate ion. If we see the nitrate ion pop up, we know again that it's going to be an aqueous solution. Okay? So if you have those two rules memorized, it drastically improves your odds of being able to predict an answer for an individual equation. The rest of them, ultimately, to go through and really answer all of these kind of questions perfectly, you'd have to have them all memorized. I don't expect you to have them all memorized. I will give you a condensed rule sheet. You just need to be able to interpret it appropriately. Okay, so what do we mean by interpret? Let's take a look at our two equations. I'm going to start with the second equation. When we look at the second equation, you'll notice the starting materials given were sodium chloride and lithium nitrate. We told you that both of those species were aqueous, but did we need to tell you? Sodium is where on the periodic table? Group 1 element, it's an alkali metal ion. That means it's soluble, according to the rule you now have memorized, because you're that quick at memorizing. Lithium is where on the periodic table? Same spot. It's a group 1 alkali metal ion. Guess what? Always soluble, which means if those ions show up, we will have an aqueous solution. That means when we get to our answer and we do our double replacement, I see sodium showing up, which means aqueous. I see lithium showing up, which means aqueous. Okay. Another thing that I'll throw in here that we didn't quite talk about, why did I not draw this out as sodium, lithium, and chloride nitrate? Okay. Remember, in the double replacement format, we're swapping the cations and swapping the anions. If we look at this, sodium carries a plus charge, lithium carries a plus charge. What happens when two positively charged species get near each other? They repel. We can't form sodium-lithium. Same deal with our chloride nitrate. Chloride's a -1, nitrate's a -1. We can't make this compound because we put two negative charges near each other. Bad mojo happens in there. Okay? So don't allow that to occur. Focus on those positives and negatives. Positives and negatives every time. Think about that when you try and set up your double replacement reactions. Okay? So we now have an understanding of how we can do our predictions. So let's take a look at that first equation. In our first equation, we have barium chloride. Could we predict that one? It's not one that we just have straight up memorized, but given the rules, we could take a look at rule number 4, which says halide ions. Okay, well, that's not very helpful, so what's the sentence above it say? Ionic compounds containing a halide ion are soluble in water. Okay, well, chloride is a halide ion. Okay, you'll notice there are some exceptions, and this is where these rules become tricky, as you get lots of exceptions in here. The exceptions are for silver, mercury, or lead chlorides. Is barium one of those ions? No? Okay, well, it stays aqueous then. That's what our rule 4 in this table says. If we look to the next one, the next species was potassium. Potassium is a group 1 metal. Group 1 metals, according to our chart, are aqueous. So that makes sense. So look at that, I gave you some correct information. If we now move to the products, let's go based off of what I told you to memorize. Okay, rule 1 and rule 3. Well, the first compound, barium chromate, doesn't fit under either of those rules. That's a bit unfortunate. However, if we move to the second compound, our potassium is a group 1 metal, which means this compound is aqueous. Since I haven't memorized all of the rules, when I now go back and look at my barium and my chromate, I am kind of at a toss-up here. Okay? At very least, I know potassium chloride's not a solid. If a reaction occurred here, it would have to be the barium chromate forming a solid. Okay? As a gambling man, I would have said, yep, it's solid because it didn't match the rules that I had memorized. Okay? If you aren't willing to gamble, then you need to go back and look at your rules. So what rule applies to barium chromate? And that might be a little bit tricky, so spend some time. I'll give you 10 seconds to look for it. So hopefully you found that we need to look for the chromate. The chromate ion is rule number 7, which says that ionic compounds containing chromate ion are generally insoluble in water. Well, if it's insoluble, that means it's not dissolved, which means we're looking at a solid. Okay? There are exceptions. Those exceptions are rule 1. Well, what was rule 1? Alkali metals and the ammonium ion. Barium is not one of those. So that does not satisfy our exception rule. This compound has to be a solid. Okay? So it takes a little bit of processing to go through and predict and see what happens with it. And you really do just kind of have to follow the rules, unfortunately. That's just the way it's going to work out. Let's see, what do we have next? We can move to neutralization reaction. So before we do neutralization, I do want to address one more concept. And I'm going to attempt to memorize this equation real quickly here, and we're going to go to a clean whiteboard and take a look at it. So we got barium chloride and potassium chromate. Okay, so barium chloride plus potassium chromate, okay, which goes to barium, barium chromate and potassium chloride. And technically also, and this is going to get kind of frustrating, but this is how we got to deal with it. This is aqueous. I didn't leave myself a lot of space here. This we said was aqueous. This we said was a solid. And this we said was aqueous. Excuse me, if we go through and balance this, we need the 2 in front of our potassium chloride. The format of the equation, so now we're going to talk about some other terms that can pop up here. What we've got as our format is the molecular format, meaning we are showing all of the molecules involved in this equation. If we have an aqueous compound, that means it dissolves in water, and ultimately it means it splits into ions. Okay, we'll talk about more ions much later, or a little bit later in the semester. So if we look at barium chloride, we're going to set this up as a new equation. Barium chloride dissolves into the ions of barium, which is dissolved in water, plus chloride, which is dissolved in water. Okay. How many chlorides were in that sample? 2. You'll notice the 2 does not translate down as a subscript, okay, because it comes back to what is the meaning of the 2. The 2 in barium chloride means that there are 2 chlorides to balance out the barium. If I now look at what happens when I put it into water, I end up with chloride. I don't put a 2 as a subscript anymore because the chloride's not attached to the barium. It's now floating free form in the solution. Okay, so I still have to balance the equation so the 2 comes out front as a coefficient. Okay, so anything that is aqueous, we can go through and run this quote-unquote reaction for. So we can now move to our potassium chromate. Well, our potassium is potassium ion, K+, which is now aqueous, and chromate, which was aqueous with a -2. Again, the 2 in our formula potassium chromate does not come directly down as a subscript, because the 2 in potassium chromate means there are 2 potassiums to balance the chromate. Well, if potassium is no longer bound to the chromate, I can't put the 2 there. The 2 is going to come in as a balancing of that equation. So what we're looking at is now an equation within the equation. Okay? We can then move to our next process, which is our reaction arrow. And we're going to hit kind of a hiccup here. If it's aqueous, it dissociates into the ions. What if it is any other phase? Well, any other phase doesn't dissolve in water, so we don't break it up into the ions, which means barium chromate, being a solid, cannot break apart, and I have BaCrO4 solid left. Can't touch it. Okay? We then move to the next species, which is our potassium chloride, which will break into potassium ions, which are aqueous, and chloride ions. I apologize for running out of space here, which is aqueous. We do still have to make sure our equation is balanced. So what we're looking at is this new equation here. Okay? In that new equation, there are 2 potassium chlorides, which means when I dissociate into the ions, I need how many potassiums? 2. How many chlorides? 2. So what I need to go through and do is make sure that that 2 translates down into my equation, and I have a 2 and a 2. What we have now in this format is what's referred to as the total ionic format. Ionic because we've shown the ions all the way through the equation. Okay, this format is awful. Most people hate this format. I agree with you. It's an awful thing to do to people. What we now want to do is simplify this. Does anything show up the same on the reactant side as on the product side? If it does not show up the same, then we draw it on our next line down. So let's start with the leftmost. We have barium plus 2 aqueous. Do we have barium plus 2 aqueous in the product? I see barium, but is it barium plus 2 aqueous? All of those conditions must be met. So no, that ion does not show up on the product side, which means I cannot cancel it out. So I'm just going to repeat. Okay. I move to the next one. I have 2 Cl minus aqueous. So I now look to the product. Do I see Cl minus aqueous? Yeah, I do, sort of. Way off in that little corner. And there just so happens to be 2 of them, which means I can subtract, and those 2 terms cancel out of my equation. I don't write them down. Next one, potassium ion aqueous. You'll notice that that also shows up on both sides of the equation in the exact same state, which means I can cancel those, so I don't draw those on the next line. The last one on my reactant side, I have chromate, okay, our CrO4 minus 2. I do see CrO4 on the product side, but it's not CrO4 minus 2 aqueous. It's bound to the bromine, which means I can now write that on my lower line. This can now go to the product of barium chromate O4 solid. If I went through and did my reactants very carefully, once I hit the reaction arrow, anything that's not crossed out on the product side I should just copy down. What we now have is what is known as the net ionic equation. We go to this format because what we're trying to do is remove all of the ions that had nothing to do with our overall equation, or the reaction itself. You should go through now and attempt this same thing, come back here, this same process with this last equation, the sodium chloride aqueous, the lithium nitrate aqueous, and see what happens for your final result. Look at your net ionic equation. Okay, so spend some time, go ahead and pause the video. I'll give you 5 seconds to pause here. Hopefully you've now gone through and actually done your processing, and you should be coming back wondering, why'd you have me do this? Because I just crossed everything out of my equation. I have nothing in my net ionic equation. Well, what does that nothing mean? No reaction occurred. Okay? No change in phases, no colors, nothing. That means nothing happened. No reaction. Okay? So that's kind of the pseudo goal behind going through and looking at the net ionic equation. Highlighting the fact that a reaction occurred, or highlighting the fact that no reaction occurred. And that's kind of our result out of our double replacements. Okay? So you need to go back and have your solubility, use your solubility rules when solving those kinds of problems. Last reaction that we'll mention is really just a special case of the double replacement reaction. It's referred to as a neutralization reaction. It's the reaction of an acid with a base. You already know how to recognize your acids. So that's something with an H in front of it, and we would also see the aqueous. Okay, remember our phases would be supplied to us. We'd also see an aqueous here. Ba almost always comes out as aqueous, and we end up with HOH, which is also known as H2O. Would we call H2O aqueous? No, that's saying water is dissolved in water. It's kind of an odd thing to state. Really what we're saying is that we have a liquid. Okay? So if we look at our net ionic equation for a neutralization reaction, what you'll end up finding is it'll follow the general format H plus OH minus to make H2O. Okay? So we are taking something that is reactive and charged, a positive and a negative, and we turn them into something that is neutral. Hence the neutralization reaction. Okay, so let's take a look at an example here real quickly. Let's predict the product of the complete neutralization of sulfuric acid with potassium hydroxide. You still need to be familiar with your nomenclature rules. What we're starting with here is H2SO4 aqueous plus potassium hydroxide, KOH aqueous, goes to, we're doing the complete neutralization, so every hydrogen that's attached to sulfuric acid needs to be swapped out and put with our OH from our water. Okay, so we're doing a double replacement reaction. Potassium needs to combine up with SO4, and our H needs to combine with OH, okay, to give us our H2O. Before we continue, are our formulas balanced? The charge on potassium is a +1, the charge on sulfate is a -2. Our charge is not balanced, we need 2 potassiums, so we're adjusting the formula. That needs to be present. The other thing that we kind of have to remember is we go back to those rules that I told you to memorize for solubility. Potassium is a group 1 element. It's aqueous. If we take a look at our HOH, that balance, H is a +1, OH is a -1. Our formula is balanced. The phase in that case, as we just talked about, is a liquid. Is our overall equation now balanced? Well, we'd go through and say, starting with potassium. Potassium has 1 on the left. Let's go with a different color. Oh, that looks horrible. Let me just erase all of that and try again. If we start with our potassium, 1 on the left, 2 on the right. So we need to make sure that we have 2 on our left. Alright, the next thing that I would balance would be sulfate, and because sulfate doesn't change in the course of the reaction, I can get away with this. We have 1 on the left and 1 on the right, so that's balanced. I can look at my H. Okay, this gets a little bit tricky on trying to decide where that is, and in fact I'm going to back away and say I'm not going to look at H, I'm going to look at OH. Okay, so I'm looking to balance hydroxide right there. There are 2 hydroxides in that formula. If I go over to my product and look here, there's only one hydroxide. What do I need to do? I need to make it 2 by putting a 2 in front. Okay, if you're not comfortable with this version of it, then what you should go through and do is break it down into potassium, sulfur, oxygen, and hydrogen and attempt to go through and balance. It is much more challenging. Last one, hydrogen. We have to be careful with this because it's not hydrogen in OH, it's just the hydrogen here. There are 2 hydrogens on the reactant side, and it's just the hydrogen in front because I've accounted for the other hydrogen in hydroxide. I have 2 hydrogens in the product. I can now go through and check, and we'll verify that I am correct. Okay? Again, this is tricky because we're now pulling out the complex ion that includes hydrogen. Okay? And hydrogen shows up in another place. So you got to be a little bit careful when you go through to balance ones where your elements show up in multiple different places. It definitely makes it trickier. We run into the same issue with the oxygen because the oxygen shows up in multiple different places. This is one of the reasons why I did not write H2O. I left it as HOH because in HOH I can see a little bit more clearly that that is the combination of hydrogen with hydroxide. So it better reflects the double replacement reaction. Okay? So it's kind of a simplification that you can go through and do to kind of help you with that. That is the end of our neutralization or our Chapter 7 material. So now what we're doing is moving into Chapter 8 and Chapter 9. A lot of the concepts in both of these chapters overlap, so they're kind of coming all over the place with these. This is going to be a strong dimensional analysis chapter. So back in Exam 1, everybody was complaining about all the numbers. We're coming right back to those numbers, and we're going to bring in some new units that everybody's going to freak out with as well. Okay, so remember, all we're trying to do is do a conversion. So figure out what your conversions are and just start doing them. In Chapter 1, we maxed at probably 2 or 3 conversions. We'll probably run up to 4 or 5 conversions in the worst case through Chapter 8 and Chapter 9. Okay, so be careful with that. I'm going to try and keep them separate so you can see what's going on with it. The intent is going to be to run just lots of practice because there really isn't anything else beyond just practice on getting through Chapter 8 and Chapter 9. Once you know what your conversions are, it's just crunch it out. Okay, so let's go ahead and get started with that. Standard kind of metric conversion. I will go through and work this one with you right now just to get you kind of refreshed. So with our general process, we can read our question. What is the mass in micrograms of a 325 milligram aspirin tablet? So what we would do is start with where we want to be. We want a mass, so we're going to have equals, and we want micrograms. We need to know the symbol for micrograms. It's the funky, that was funking looking U. And we started with 325 milligrams. So ideally, what we would do is take a look, multiply by some conversion factor. We want to get rid of milligrams because it doesn't show up in the answer, and we want micrograms. Okay? So now we think, do we have a conversion factor that allows for this? Okay? Depending on your level of understanding and manipulation with these, maybe you do, maybe you don't. Okay? I would argue that you don't. Okay? At least how we've been talking about it. Okay? So that means that conversion doesn't work. Can we convert milligrams to something else in the hopes of getting to micrograms? Well, we could try and go to grams. Okay? That conversion you should know. Milli meant 10 to the minus 3. So if milli means 10 to the minus 3, I can put my 10 to the minus 3 in front of my base unit, which was grams, and 1 in front of the milli. This means my milligrams cancel. I now have grams, so I have a new unit conversion problem. Grams in the denominator because I want the unit to cancel and I want to get to micrograms. Okay, this is a conversion that you may again not know. So on an exam, what you should do is flip to the front of the exam. Okay, the milli one you need to have memorized. I told you to memorize it. If you've already forgotten it, memorize it again. So you need to memorize your milli. I spell memorize, there it is. So you've got milli, kilo, and centi. You need to know those. Okay, so that's your M, little k, and c. The microgram is not one I've told you to memorize. So if we take a look at the front of the exam, you will probably see that 1 microgram is written as equals 10 to the minus 6 grams. So where do we go through and put our numbers? Well, the 1 showed up in front of our micrograms in our conversion factor, so we put the 1 there. The 10 to the 6 showed up in negative 6 showed up in front of the grams, so we put the 10 to the negative 6 there. When we now go through and track our units, our grams cancel, and we end up with our final answer of micrograms. We can now go through and plug this into the calculator. As far as the calculator work goes, I would multiply everything in the numerator, so everything up top, so 325 times 10 to the minus 3, and I'd get a number in my calculator. Okay, so let's just say number. I would then go through and do the denominator. The denominator is 1 times 10 to the minus 6. I get a number for my denominator. Oops. Now that I have these two numbers, I now do my final calculation, which is the number in my numerator divided by the number in my denominator, and I'll get my final answer. That's just personally how I would crunch through it. If you got a different way, feel free to go ahead and do that in a different way. Okay? So, remember your dimensional analysis. Write down where you're trying to get to, and write down what you're starting with. And then just attempt conversion factors, always trying to progress towards your final answer, okay, as best you can. And if you get a wrong step, that's fine. Just erase that step, go backwards, and try a new conversion factor. You will still find that even at this stage, there's really only one conversion factor as a possibility. You don't have that many options to convert out to something else. Okay? So if you've got a conversion, just drop it in there and see what happens. And then drop the next one in and see what happens until you get to your final unit answer. So track the units. You'll notice all the way through this, I did the units first, then I dealt with the numbers. Okay? The units will get you to the answer. Do not use numbers. Okay? The only time you can do a number is when your units say you have the answer. So, where Chapter 8 is really going into this is if we take a look at the scale of our experiments. Okay, so this woman, I believe, is what's going on here. I think she did this. She built Hogwarts because she really liked Star Wars. So she built the castle in Star Wars out of Lego bricks. And we could go through and do an experiment here and say, okay, well, how many Lego bricks was that? Okay, you're looking at thousands upon thousands upon thousands of Lego bricks probably. So what we want to do is potentially come up with a new unit to explain how many things went into it, or even how many hours went into the design and building of this. Okay, that's ultimately what chemistry is doing. When we look at an individual reaction, we're looking at putting thousands upon thousands upon thousands of molecules into an individual reaction. Okay? With all of those molecules, we don't want to deal with numbers that big, so we can create a new conversion factor to allow us to understand it a little bit better. And yes, I'm aware it's not Star Wars, I was just kidding. So, numbers, concept, and equations. A farmer has 72 chickens, and each chicken lays 2 eggs a day. How many eggs can the farmer collect per day? So let's just crunch it out. Okay, so if we look at our problem, we're looking at eggs as an answer, and we're really looking at eggs per day as an answer. Okay, So if we look at our units that we're starting with 72 chickens. Okay, super exciting example. Well, in my conversion, come back here, I want to get rid of chickens, and I want, as a unit, eggs per day. Okay, am I given a conversion factor that allows me to do this? Well, it says each chicken lays 2 eggs per day. Well, each chicken means one chicken lays 2 eggs per day. So, crunch out the math, I get 72 times 2. Not too bad. We get 144 eggs per day. Cool. Well, our farmer's kind of a special person. He has a very hard time dealing with any number bigger than 15. Let's just pick a random number. So anything bigger than 15, he cannot comprehend. Okay, it just doesn't make sense. Well, I got a better number. Any number bigger than 20, he can't understand. Okay, well, why does he have a problem with it? Well, he understands 20 because he has 5 fingers on his left hand, 5 fingers on his right hand, so he can get to 10. And then if he's got to go further, he'll take his shoes off and he'll count 5 toes on his left foot and 5 toes on his right foot. So he can get 20. He understands 20 great. But anything bigger than 20 can't understand, doesn't make sense to him, and he thinks you're ripping him off. Okay? So we need to come up with some way that he can understand this number better. Okay? So is there a way we can convert this 144 eggs per day to something less than 20? Okay, and I'll give you a couple seconds, minutes, something like that to think about this. If you were told to go to the store and buy some eggs, okay, typically what would you do? Do you go into the store to buy 3 eggs, 2 eggs? Okay, you typically go to the store and you'd buy what? 1 dozen eggs. Okay, well, what is dozen? I don't understand what dozen is. You can't tell me to buy a dozen. I'm not going to walk in and not be able to understand that. So what is 1 dozen eggs? Well, 1 dozen eggs equals 12 eggs. Okay, what can we do with that? Well, can we convert this 144 eggs now into something else? Can we convert it into a dozen? Well, 1 dozen equals 12 eggs. So we can explain to the farmer that a dozen is 12 eggs. So he goes, okay, I can understand 1 and I understand 12. Sure. You can then punch out or bust out your calculator. Don't punch out the farmer. He might be upset by that. Okay? And we do our calculation and we end up with now 144 divided by 12, which hopefully I'm right, is 12 dozen eggs per day. We've now converted this number of 144, which was incomprehensible to our farmer because he doesn't have that many toes, okay, or that many fingers, to now a number that he can understand. Because, well, that takes 2 hands and 2 toes off my feet, and I can get that many dozen per day. Wow, okay, now I'm producing a lot. And he can start to understand and comprehend this number. Okay, so that's kind of what we're going to get into when we bring in the concept of a mole. Okay, it's the same thing as a dozen. Okay, so the dozen is something that we're allowed to, or we can use to manipulate. Okay, we can use this same concept when we come back to equations. If I look at trying to build a bicycle, and I've been practicing on my drawing here, so hopefully this will come out okay. If I'm going to build a bicycle, I need that frame and I need my bicycle tires. Okay, and let's just assume it's got the handles. There's the handle, there's a little seat. Okay, there's even a little pedal thing. Okay, if I'm going to build that bicycle, I can look at the pieces that went into it, and what I decided to do is just break it down into the tire and the frame. So I look at this and I say, okay, if I'm going to build a bicycle, I need one tire and one frame. Is my bike going to go anywhere? Probably not. You think, oh, that's a dumb example. Clearly you need two bicycle tires. Okay, well, thank you. I appreciate your concern for my mental well-being. Yes, we need two tires and the frame to build the bicycle. How do we know that? Well, clearly, come on, as a teacher, don't you understand that there's two tires there? Of course you need two. Okay, thank you, I agree with you. Okay, we do need two tires there. Okay, this equation that we've just drawn out here is the same thing as our reaction equation. It tells us how many pieces, or the number of atoms, that we need as reactants to make a final product. If we were going to compare this back to the reaction types that we just discussed, what type of reaction just happened to make this bicycle? Tricky question, so go ahead and give it a shot. I'll give you 5. We have a combination reaction, because we took 2 units and we put them together into one. So we got a combination reaction. So we can do these parallels into the real world. It becomes very difficult when we move into chemistry because what we're looking at is things at a very tiny scale. So realize that tiny scale does make things a little bit more challenging. Okay? So, the equation concept and now its potential weakness. So let's take a look at the equation given here. You should notice that before we can even answer the question here, we've got some work to do. How many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? Okay, well, this is a combination reaction just like the bicycle. And to build the bicycle, we had to first make sure that our equation was balanced. So we'll first have to go through and make sure this is balanced. And if we check, you should notice that we need 2 sodiums to balance out this equation. So we need that 2 there, and then everything else should balance out for us, okay, which it does. So now when we go to answer this question, how many molecules of CO2 are necessary to make 2 molecules of sodium hydrogen carbonate? Well, if we look at the equation, how many molecules of CO2 are needed to make 2 of the sodium hydrogen carbonate? Okay. What we're looking at is 1. Okay. Said another way, let's put it into an equation format, our dimensional analysis. I want to make molecules, which I'm going to abbreviate MLCS, of CO2 are necessary to make 2 molecules of our sodium, hydrogen carbonate. Okay, so there's all our information. We wanted to go through and do a conversion. What's the conversion? Well, molecules of sodium hydrogen carbonate need to disappear, and we need molecules of CO2. Well, what numbers do I put in front of them? Well, what number showed up in front of molecules of sodium hydrogen carbonate from our balanced equation? Well, it was 2. What number shows up in front of molecules of CO2? Oh wait, I don't see anything. So that must mean it's 0. If it's 0, then it wasn't there. So we imply a 1. So what happens when we go through and do our calculation? We end up with how many molecules of CO2? 1, which you were probably already able to do just by looking at the equation. So that's kind of a neat process. We can use the equation to predict how much of something we're going to make by using a conversion factor that comes from the balanced equation. Okay, so use that information. That's why we balance. Okay, so now the next question. What is the mass of 2 molecules of CO2? Okay, well that's a little bit more challenging. Okay, and I've given you this thing AMU, and we haven't really talked about that yet because it is very misleading. Okay, AMU is just your mass unit. So where do we find anything about the mass of a molecule? Well, if we look really carefully in the room that we're in for our lecture, we should see two giant things on the walls. We've got a periodic table of the elements. And we've got on that periodic table the atomic number and the atomic mass. Well, the atomic number was what? Number of protons. The atomic mass was the number of protons plus the number of neutrons. Okay? When we added those two values together, we got the mass, okay? And in fact the atomic mass, okay, that's what we decided was our atomic mass, so just the number of protons and neutrons. So we call that our atomic mass unit because it's not really a mass, it's just the addition of a bunch of atoms or a bunch of particles with no real mass unit. So we refer to this as the atomic mass unit, or AMU. Okay, what we're about to talk about is something else, known as the molar mass. Turns out that the atomic mass and the molar mass are very related. Our atomic mass is just the average of protons and neutrons within a given element. Okay, our molar mass is now going to be the mass per mole. So our atomic mass was the mass per atom. Our molar mass is the mass per mole. Okay? That's all it means. And we're going to come back to that in a little bit. So, if we look at the mass of two molecules of CO2, all we have to do is look at the mass of carbon, which is 12, okay, and the mass of oxygen, which is 16. There's two of them, so we get 32. We add those numbers up and we get a mass of 44 AMUs. Okay, and I'm kind of ignoring sig figs at this point. So there we go. We've got the mass of two molecules of CO2. Well, when we go into the balance room, we can start to measure out the mass of CO2 in AMUs. Except our balance doesn't measure AMUs. Okay, valid point. So let's just figure out how to measure it in grams. Okay, so what's the conversion between grams and AMUs? Well, that number's in the lower right-hand corner of your screen. So we could go through and try and set this up. We just said our mass of CO2 was 44 atomic mass units. Okay. Oh, and if we wanted two molecules of it, there's a problem. We have to multiply by 2. So we'd have 88 AMUs. Okay, so that's what we're starting with, 88 atomic mass units. And we want grams of CO2. Well, so we set this up. AMUs need to be on the bottom, and grams of CO2 need to be on top. The number that shows up in front of grams is 1.661 times 10 to the negative 24th, and AMUs is 1. We just multiply that out and we get a stupidly tiny number. Okay? It's a bit challenging. If we were going to go through and measure out just two molecules of CO2, that is such a tiny, tiny number that we can't actually weigh it. So if we wanted to run an experiment to prove that we did our balanced equation right, we've got a problem. We can't actually weigh this amount. Okay? So we have no ability to do this. Okay? And this is where, as chemists, we said, okay, well, we won't measure it at that small. We'll measure it at a much larger amount. But then that means we have to use somewhere on the order of 10 to the 23rd molecules, or 10 to the 23rd atoms, right, to get a mass reading that's reasonable. So 10 to the 23rd molecules, or atoms, for an individual reaction. That's a lot of atoms. So that means when we go up here into our reaction, we need 10 to the 23rd of these, 10 to the 23rd of these, 10 to the 23rd of these, and then 2 times 10 to the 23rd of those. Okay? That's a lot of zeros in our balanced equation. And I don't know about you, but I don't want to deal with those numbers, and I don't want to deal with those exponents. So we have to come up with some way to simplify this. Okay? This is where Avogadro came along a long time ago and said, you know what? We can't run experiments on that scale. on the atom scale. So we're going to run it on a much larger scale. And that larger scale, he decided to measure it out as and define as a mole. And that mole, he said, was 6.022 times 10 to the 23rd atoms. This is a massively important number. It pretty much deals with all of our conversions and makes everything beautiful and fantastic to work with. Okay? So this scale allows us to actually measure solids to an appropriate amount. Without this conversion factor, we have no way of really making good use of our equations, because we end up having to use too large of a number for each of those equations. Okay? So how can we use this number real quickly as a conversion? Okay, well, if I give you 3.42 times 10 to the 21st atoms of aluminum, how many moles is that? Okay, we'll set up the problem. Whoops. We always start with what we want. We want moles of aluminum, and we start with 3.42 times 10 to the, what did I say, 21st atoms of aluminum, and I want to get over into moles of aluminum. So I need to do some conversion factor where the atoms of aluminum need to cancel and moles of aluminum need to be in the numerator. Well, do I have a relationship between atoms and moles? Oh, fun, look at that, it's even in red. Okay, well, 1 mole happens to be 6.022 times 10 to the 23rd atoms. Okay, well, that's a big fancy number. That might be a lot of effort to go through and memorize. While I am going to highly recommend that you memorize it, I will provide you that number on the exam, okay, because I'm such a nice person. When we go through and do that calculation, we now just have to divide those numbers and we get our final answer of moles of aluminum. Notice again, when we set this up, we'll go through the same patterns. What do we want? What are we given? What units can we use to cancel out? Now what numbers do I need to put in front of those units? Okay, each and every single time. Okay, I'll leave this to you to go through and do on your own. So how many oxygen atoms are in 0.240 moles? Okay, mole of several substances. You'll notice that we don't get the same volume for each of these, which should make sense. We shouldn't get the same volume because what we're looking at is different species with different densities, different masses to that volume. Okay? So a mole can be a lot of different things as far as sizes and shapes go. Okay? Mole calculations. So we really need Avogadro's number ultimately to give us mass, okay, or reasonable mass. Okay, reasonable experimental masses. That's really the only reason we're using Avogadro's number. Okay, reasonable experimental masses. Okay, so it comes back to how do we measure our reactants? We measure our reactants most commonly through mass, so we need Avogadro's number to account for that mass appropriately. Okay. We talked about this whole AMU issue, and I said we were going to come back to it. We can use Avogadro's number to determine the molar mass off of our periodic table. So this is where it gets kind of interesting. Okay, so let's see, what is the mass of 1 mole of carbon atoms? Okay, well, we said we can use the periodic table to determine the atomic mass. Whoops, go away. Our atomic mass for carbon was 12 AMUs. Okay? And that's the mass per 1 atom. Okay? And where I'm trying to get to is the mass, okay, and I meant to specify the unit, but I didn't, the grams of carbon in 1 mole of carbon. Okay, so that's my end goal. So we've got a conversion factor that we're starting with and that we're ending with, so we can really go a bunch of different ways with this. Okay. I personally, for some reason, like to deal with the numerator first. My numerator doesn't match, so I want to fix that. I want to get rid of AMUs and I want grams. Okay, and as a complete unit, I should specify the carbon for each of those. Do I have a relationship between grams and AMU? Turns out we do, upper left-hand corner. Okay, this is one that I will probably give to you as well. Okay, and we'll see how I'll give it to you in just a second. So 1.661 times 10 to the negative 24th grams is 1 atomic mass unit. If I now follow my units, I will have grams per atom. Well, I want grams per mole, so I now need to go back to my conversions. I need to get rid of atoms, so I'll put atoms as the unit on top so that it cancels way back at the beginning. And I want moles on the bottom. Again, complete unit, atoms of carbon, moles of carbon. Is there a conversion factor between the atoms and moles of an individual species? Yeah, we said there were, according to Avogadro's number, 6.022 times 10 to the 23rd atoms per 1 mole of carbon. Okay, so we've now set it up. We've got a relationship between our AMUs per atom and our grams per mole. Okay, this conversion is neat enough that I'm actually going to give you a few seconds here to bust out a calculator, and I actually want you to calculate the number to come out of this. Okay, and I won't even pause the video. I'll just give you 10 seconds. Get your calculator, crunch it in. Okay. We went through all that work. What'd you get for a number? 12? What? But isn't that what you started with? It is. Guess what information your periodic table gives you? Not only does it give you your atomic mass, it gives you your molar mass. So if we look at the periodic table for, say, the molar mass of oxygen, just an oxygen atom, we look at it and we see that the atomic mass is 16 AMUs. Right? Well, it turns out that the molar mass for oxygen is 16 grams per mole for oxygen. Hey, that's pretty cool. So our atomic mass on our periodic table is one and the same as the molar mass. So if you're ever asked anything about the molar mass, you can now find it on the periodic table. Remember, the units of your molar mass are grams per mole. It's your complete unit. So it's a conversion between the mass and the moles, or the mass of an object and the amount of that very same object. So it's a nice little handy-dandy conversion. Our periodic table is pretty freaking sweet. Okay? So we get the same thing. Fantastic. And that's really what you should be thinking about when you see the periodic table, is the grams per mole, not the AMUs. So we kind of wash atomic mass units out of your head now. So, conversion factors. The rest of Chapter 8 and Chapter 9, barring anything to do with volume, so ignore volume entirely. You don't have to worry about anything that shows up with volume. We now have ways to convert between things. Okay? So this lists off where you can find each of those individual conversions. So measurement conversions, if we want to convert, say, grams to pounds, there's tables of those in your book, so you need to go to your book to find them. As far as the exam goes, within the metric system, you have to have it memorized. So memorize those important conversions. The ones I told you to memorize, again, just in case you forgot, were the kilo, milli, and the centi conversions. You need to know those. The English conversions, I will provide you those on the exam. So that'll be on the very first page, just like with every other exam you've seen. Okay? Exact same conversions, maybe a few extras. The number of atoms. So if I wanted to figure out the number of atoms per some structure, I can find that information from a formula. That formula must be balanced, because if the formula is not balanced, I can't determine the proper ratios or the proper conversions. So as an example, if I want to know the number of sodium atoms in sodium sulfate, I would look at my formula for sodium sulfate that is balanced and say within sodium sulfate I have 2 sodium atoms. So as a conversion factor, if I want sodium atoms and I know sodium sulfate, there is 2 atoms of sodium per 1 molecule of sodium sulfate. There's my conversion factor, okay, that I can now use in any equation. We can do the same thing with magnesium chloride. How many magnesium atoms are in a molecule of magnesium chloride? Okay, well, atoms of magnesium versus molecules of magnesium chloride. Well, there's one atom of magnesium in one molecule of magnesium chloride. So you're given those conversion factors. They're just kind of buried a little bit. They're a little bit hidden. So you got to dig them out a little bit. Okay? If we move to the next one, we can get the number of molecules. And we can get that from a balanced equation. Okay? This one's a little bit different, okay, from number of atoms. Our number of atoms really comes from a formula. But we can now use a sequence of formulas in a balanced equation to actually convert between species. Okay, and that's kind of a fascinating thing. If I want to convert iron plus 3 into iron plus 2, I can now do that from this balanced equation. Okay, and as long as I'm using this balanced equation. So if I have iron plus 3 and I want to convert it to iron plus 2, well, the number of molecules of iron plus 2 needs to be in the numerator, and the molecules of iron plus 3 needs to be in the denominator. Okay, without a balanced equation, I have no way to relate those two. But with the balanced equation, 2 molecules of iron plus 3 become 2 molecules of iron plus 2. I now have a way to convert those species. So the balanced equation, wicked awesome to give us yet another conversion factor. Okay, and more importantly, it allows us to convert between species that are changing. I don't have to convert to, say, even the same element. I could convert to tin, okay, plus 4. Okay, that means when I go back to my conversion, I want tin plus 4 in my numerator. What number should show up in front of those? Well, if we look at tin plus 4 in the product, the number in front of it is a 1. If we look at iron plus 3, where it shows up in the equation is a 2. Okay? So I can convert using this equation. Okay? So that's kind of cool. The balanced equation gives you that conversion factor. You have to needle that information out of the equation. Before you can get that information, what do you need to have? You need to have a balanced equation. If your equation's not balanced, all your information or all your work after that is going to be wrong, which is why we've talked about balancing equations a lot, because you need to be able to balance it, okay? Because we have to use that information further on down the line. The last sequence of conversion factors that we can get is the number of moles, and we can get this from atoms and molecules. So we could go back up to our equation for our formulas. Let's say I want to know the number of moles of magnesium per the moles of magnesium chloride. Okay, well, moles is just another way to say a different number. Okay, so if I refer to now this structure as 6.022 times 10 to the 23rd magnesium chlorides, I can convert that into 1 mole of magnesium chloride is now 1 mole of magnesium. And that's because the numbers associated with each of those come straight out of our formula. 1 in front for our magnesium chloride, and the 1 subscript from our formula. Okay? So we can take advantage of that from our atoms and our molecule information, even from our balanced equations. Okay? The last place that we got to watch out for converting our moles is we can use Avogadro's number. That's our 6.022 times 10 to the 23rd units, equaling a mole. Okay? You'll notice that a lot of general chemists throw up this big hoopla about, oh my gosh, the mole is so amazing, 6.022 times 10 to the 23rd, and all this fancy stuff. And October 23rd was however long ago, and at 6:02 a.m. everybody threw this big giant party as chemists, and we're all happy and fantastic. I'm not going to lie, the mole is an important concept. Okay? But it's a concept that once you use it, we don't care about the number anymore. We just shift to using moles, and we're done with 6.022 times 10 to the 23rd. So it is our fundamental building block on which everything else is based, but once we know that, we stop using it. Okay, so you really only see this whole mole number as a popularity thing to make everybody think chemists are cool. I don't need to think chemists are cool because I already knew that. You know, I say that every morning when I wake up and stare in the mirror. And every morning I walk out super proud and happy to be an awesome person. Sort of. Did I record that? That was awful. Let's try again. Atomic or molar mass. Our grams per atom and our grams per mole can be found from the periodic table. Remember, just like we said, the Avogadro's number is pretty much useless once you get beyond the concept of actually getting into the lab and using anything. Same thing's going to happen with your atomic versus molar mass. Really the only important one is the molar mass, which is your grams per mole. And you'll be pulling that off of your periodic table most frequently with all of your conversions. Okay. The rest of the slides in this presentation, I'm fairly certain, are just conversion practice. Okay. So I would highly recommend that you go through and take a look at these. I'll run through, give you about a 5 to 10 second chance to pause the video so that you can look at these slides if you don't have them. If you are currently taking the class with me, these slides are available from the online Canvas site, so you can download them there. And you should go through and attempt to work these problems. We will be working through them in class both on Tuesday, and I will probably pull some of these questions out into slides, or not slides, into the in-class activity for the Thursday class that I will be missing, that you'll have a substitute for. Okay? And she can help you go through and look at each of these conversions and allow you to help piece them together and get to the correct answers. Okay? Hopefully you don't have any questions and you really just need to go through and do some practice. If you do have questions, make sure you write them down, so Tuesday in class, when I start clicking through the slides saying, are there any questions, you can be like, yep, there's a question, and I'll go through and answer that. Okay? And I just forgot, I do have a little bit more on Chapter 9. We already talked about it. It's looking at the balanced equation and allowing us to convert between things. So we can get a bunch of different factors coming out of our balanced equation. Okay? So this gives us all of those unit factors. Just another way to look at it, how your textbook likes to talk about it. Figure we might as well include it. Thank you for listening, and I will see you on Tuesday.